Today we're going to look at the parent graphs and then transformations of the parent graphs for exponential and logarithmic functions. So when we did parent graphs, these were the other two that we skipped besides rationals. So now we'll go into all the left, right, up, down, vertical stretch, shrink, reflection, all that good stuff. We're going to start because, the function is y equals a to the x, meaning a can be any base. I'm going to specifically assign the base to be a 2, just so we can get a graph of some real points. Now we are going to use the calculator for this, but I want to graph the parent function without the calculator. Let's graph a little bit of everything. Negatives, positives, zeros. So when you put 2 to the negative first, a negative exponent creates a fraction. So that 2 to the first gets shoved to the bottom, and of course you can't leave the numerator blank, so this is really 1/2. It's not a negative number, it's a fraction. And then when you have anything to the 0 power, it's of course always a 1. That's essential. Anything to the 0 power is 1. That's going to be a big part of how our graphs work. And then 2 to the first power, rather, is obviously a 2. So let's plot these points. We have negative 1, 1/2, 0, 1, and 1, 2. So we already know that there's an asymptote right here just because we've studied this parent graph before. And of course, this is what exponential growth looks like. As you go from left to right, it starts to grow, and it grows rapidly. Of course, over here on the left side, it grows very, very slowly. As soon as it hits that y-axis, the growth changes and grows a lot. The domain of this graph is all reals, or negative infinity to infinity. The range is from 0 to infinity. It's not allowed to be 0, but it can go obviously up to infinity. We have no x-intercept. And the y-intercept is 0, 1. And this is again because everything to the 0 power equals 1. And we do have an asymptote at the line y equals 0, or you could call that the x-axis. This is actually exponential growth. Exponential decay looks like it's going down as you look at it from left to right. Same kind of pattern, asymptote, y-intercept up 1, but as you go from left to right, it decays. So that's exponential decay. We'll go over how you know which one it is here in a second. Now we are going to graph these with the calculator, but we kind of already know what's happening. We're going to graph them with the calculator because we're just looking for some patterns. So when you put this in the calculator, when you hit the power key, like when you go 2 and you hit the power key, if your power key looks like that, you are going to have to use parentheses around the power. When you hit the power key, it actually gives you this little box up here, then of course you don't have to use parentheses because you'll see that it's all in the same thing. So we're just trying to look for some patterns here as to what's actually happening. If you look at the actual graph, it does look like the parent function, and if we look for the y-intercept, it's a little bit higher. So the y-intercept isn't at 0, 1, it's actually at 1.125. So it has moved up a little bit. Also, if you look at the graph, it's moved. We have a good point here at, looks like 3, 2. So let's draw this in here. First of all, you already know what this does. That moves it up 1. So by moving it up 1, we take this asymptote, we move the asymptote up 1. The asymptote is necessary. It'll help us draw the graph a little bit better. So we know that this is kind of the guideline for the graph, and that's where it starts to break. That minus 3, well, our y-intercept is supposed to be right here, and it got moved 3 to the right. All right, so this point that is our new y-intercept really isn't from the parent graph at all. This is our y-intercept. Our y-intercept got moved to the right 3 and up 1. Of course, the asymptote did as well, got moved up 1. Excuse me, if we take a look at this next one, here we have kind of two numbers. We have this number out in front. Normally a number out in front creates a vertical stretch or a shrink. Let's see what happens when we graph this. We already kind of know what's going to happen with this x plus 2. All right, I'm assuming that if the minus was to the right, this will be to the left. And that's exactly what happens. So it did not move up or down, so our asymptote is still right here. And our y-intercept, which is supposed to be right here, actually moves to the left. But because of the vertical stretch, it gets stretched. So it gets stretched and pulled up, and of course it's moved over. So our new point we're really looking at is at -2, 4. Because it got moved to the left 2, and it got stretched. It was supposed to be at 0, 1, and we multiply that by 4, it moves it up to 0, 4. Now, just because it is the graph, we probably should have another point on here to sort of plot to get the good curve. Let's go with the -3, +2. All right, so we know that that's where our asymptote is, and so we can see and actually put the kind of this, it's actually a good stretch on there. Now for this last one. Graph it without the negative sign first, so we can get an idea as to what's happening. We know what this negative sign does. It obviously reflects it around the x-axis. That's just what it does. It's for every graph. But with the fractional base, what happens is this becomes exponential decay. And exponential decay looks different. Of course, so we've got a lot going on here. We got the -2, so we know it's going down 2. So we know we're going to take this asymptote, and we're going to move the asymptote down 2. The graph, without, and I'm just going to sketch it on here, without the reflection, it looks like this, because it's exponential decay. Now that's not exact, right? I just drew it on there just to show you that it does look like it's going downhill. So when we go to flip it over, we've got to make sure that we understand that it's going to look like this. All right, because it's going to be a reflection. So because it's exponential decay reflected, not exponential growth reflected. So let's get some points here. From the table, we have the point 0, -4. That's 2, 3, 4. I'm just going to draw it right on top of my little sketch there. We also have the point -1, -5. So my sketch was pretty close, but then this is really where the graph is. So that's exponential decay. So let's go through these parts just to confirm what we already kind of know. We know that this negative sign out here reflects it over the x-axis. We know that this creates a vertical stretch if the number is large. We're not going to get into too much of the tiny details here. Here's where the base lives, and the base can be anything. As you saw, we had lots of different examples of the base. The base controls whether it's growth or decay. Growth if it's greater than 1. Decay if it's between 0 and 1. I'll just call this my base. It's between 0 and 1. So a fraction, less than 1. Then your power, right? The power is where the variable lives. And if the power has addition, then it moves to the left. And if the power has subtraction, then it moves to the right. And then we have the one that is always good to go. On the outside of this thing, the stick out number, plus is up and minus is down. So those are the things that are controlling our exponential growth and decay curves. This is actually our last parent function. You might feel a little sad. So let's take a look at the exponential function. We're going to do these without the calculator. This is because not everybody has the ability to put this in their calculator. So just to keep it fair, we're going to not use the calculator. So we really got to study the pattern on this one. So it says for any base, the x-intercept is 1. Why? Why is that true? So let's take a look at this. Let's just take a look at some ideas behind the logs. If you just straight up do the common log of 1, you always get 0. The log of 1 is 0. So if we do log base b of 1, we get 0. So it's not going to matter what our base is. The graph always passes through b1. Well, why? Why can't I just put any base there? Well, let's take a look at some logarithms. So we have log base b of b, why does that equal 1? It's because the bases match. So the base of the logarithm matches the base of on both sides. So we have b to the first equals b. So when your bases match, right, then the powers match. So if our power is always a 1, then it's always going to go through base 1. This is a super, super important point. Base comma 1 is always on your graph. Always. Also, what's also on your graph? Always, this guy right here, 1, 0. Now, of course, if we move the asymptote, if we move this asymptote this way or this way, that's going to move that 1, 0. So apparently, the pattern, if you look at it, if we just study what this asymptote is, the first point to the right, 1 space to the right, that's what I'm talking about. So 1 to the right of the asymptote. What's the domain of this graph? Well, the domain, as you can see from the picture, is 0 to infinity. And the reason is there is no log of 0, and you cannot take the log of a negative number. So we can't have a log of 0 or anything negatives. Now the range, despite what the graph looks like, this does go from negative infinity to infinity. So don't let your calculator convince you that it doesn't exist very low. It just doesn't get drawn because the calculator can't draw it that tiny. Vertical asymptotes, of course there are. It's at x equals 0, unless of course we move it left and right. And we have no horizontal asymptotes. So these two things, super important when drawing our graphs. Now we're not going to get anything crazy because we're going to take the calculator out of your hand, so expect this pattern to be true. We're going to do that to you. Give you something that isn't going to follow that pattern. So we're going to do kind of the easier graphs. So remember our 2 points. We have to have base 1, and then we also have to go, well, what would be the point 1, 0, but we know that that means just 1 to the right of the asymptote. So knowing our patterns, anything with the letter is controlled by left and right. The fact that it's base 3 is important because we know we have the point 3, 1. So we have the point 1, 2, 3, 1. And we've moved it 2 to the right. So it is the asymptote. Oops. So by that 3, 1, what I mean by that, let me erase this, is as you count it from the asymptote. It's not actually 3, 1. We count from the asymptote. So at this point, I can't erase it for some reason. So as we count this thing from the asymptote, we go 1, 2, 3, up 1. So from the asymptote. And then, of course, immediately to the right one is the pattern that we saw. So now we have this graph right here. So that's how that works. So let's try another one. So this one is down 4. Now moving it down 4 doesn't affect this asymptote. It's still there. Now normally what we would have, right, we would have the point 4, 1, and we'd have the point 1, 0. So we'd have the point 1, 0, and 4, 1. But we got to move these points down 4. Because you can't see the asymptote sliding down 4, but we can see the whole graph sliding down 4. So we just graph these 2 original points, move them both down 4, use the asymptote and our 2 points to draw the graph. Now the domains. Here the domain is obviously starts at this 2, so this would be 2 to infinity. And the domain here would be 0 to infinity, from the asymptote to the right. So those are our important points, base 1, and then 1 to the right of the asymptote. Up and down you do afterwards, left and right. You can also do afterwards if you want to, but I do it from the asymptote. Practice the graphs on the homework. Use the calculator for exponential growth and decay, and try not to use the calculator for logarithms when you practice.